Hi and welcome to High School Physics Explained, and today I'm going to do the third installment of my answers to the HSC of 2019, and I'm going to be discussing this time questions relating to Module 7, which is about light. In my previous video on electromagnetism, I challenged viewers to, say what is the relationship of this t-shirt that I was wearing at the time to electromagnetism. Well, this is actually an image of the tracts that occur within the ATLAS detector, which is one of the detectors at the Large Hadron Collider at CERN. And these tracts show various charged particles moving through a magnetic field. And so scientists can look at these tracts, and by measuring the turn and also the radius of their curvature, we can determine their charge and also their momentum. So it's a way of identifying properties of charged particles. I'm going to now discuss the questions of the HSC for 2019 for Module 7, so let's get started. Now, before I look at questions related to Module 7, I just want to quickly touch base with question number 16 of the HSC paper. It's actually an electromagnetism question, and I accidentally left it off the previous video, so I hope you can forgive my little indiscretion there. Question 16 says, the diagram shows the trajectory of a path with a charge Q and a mass m, and is fired horizontally in a vacuum chamber, and it falls under the influence of gravity. The horizontal distance, of course, is the distance traveled. The experiment is repeated with a uniform electric field, vertical electric field, so that now the charged particle flicks upwards with exactly the same range. And we're asked what is the magnitude of the electric field? The best thing to do is to annotate the diagram so that it helps us understand what's going on. This is undergoing projectile motion, so we know that we have a force acting in the downward direction, and that force, of course, is mg. Now, in this case, we have also a force in the upward direction, and I say to you it's a net force because the net force is a combination of two forces. The first is the force of gravity. That's still acting down, mg, but then we have a force that is going to go against it to give us a net force, which we know is going to be equal to the force due to the electric field when it's applied. It has to be in the upward direction because we have a net force in the upward direction. But the fact that this is having the same range d and the same distance traveled in the vertical direction of 10 centimeters tells us something here. It tells us that the force component, that is, let's say, that component there has to be also equal, at least in magnitude, of mg, and we can call this negative if we wanted to. That tells us here that the electric field force here is actually twice this value here, because we need a net force of negative mg in the opposite direction. Now, our force due to the electric field is going to be equal to EQ. So we want to know the electric field, so we say the electric field is equal to F over Q. But we now know that the force, it's twice mg. So we get 2 mg over Q, and therefore the answer is D. Alright, now we start properly on the aspect of light. This question says a graph correctly shows the relationship between the surface temperature of a black body T and the wavelength lambda, at which the maximum intensity of light that is emitted. So we're looking really at a relationship between two variables here. Now all of this is related to Wiens Law. And Wiens Law says simply this, that the wavelength of the maximum intensity is indirectly proportional to the temperature. That is, it's a constant over the temperature in terms of Kelvin. That is, if I increase the temperature of the surface, the wavelength of the maximum intensity is going to be a wavelength that is smaller. So really what we're looking here is that if T becomes my independent variable, which is the case in all of our graphs, my wavelength being the dependent variable should show an inverse relationship. Now the only one that shows an inverse relationship is A, so therefore A is the correct answer. Question 10, in this case we're dealing with polarization, which is an aspect of the wave nature of light. Now a beam of light passes through two polarizers, and the second polarizer has a transmission angle at an angle of 30 degrees to that of the first polarizer, and the intensity is compared between I0, which is the initial input intensity, and the intensity as it leaves the polarizer. And the question is which row of the table correctly identifies the value of IB over I0 and the model of light demonstrated by this investigation. Now, this is a classic experiment that relates to the wave nature of light. There is aspects of quantum nature here. I won't go into that now, but traditionally this has always been perceived as a wave nature type phenomena. So automatically we have this possible answer and this possible answer. Now the relationship here, which is called Wiens Law, tells us that the intensity that we get in the output, which is going to be RB, is equal to the initial intensity multiplied by the cosine squared of the angle. Now we're told here that the angle is 30 degrees. So therefore IB over I0 is going to be equal to simply cos squared of 30 degrees. Now the cos of 30 is root 3 over 2. So what we have is root 3 over 2, and we all square that, so we get 3 over 4, which is 0.75, and therefore our answer here becomes A. Question 13, a laser has a power output of 30 milliwatts and emits light with a wavelength of 650 nanometers. How many photons does this laser light emit per second? Now, the fact that we've got here emit per second, that relates to the wattage. So if I wanted to talk about just simply in terms of energy, I can ignore the per second here and talk about here in terms of joules. The first thing we need to determine is the fact is that the energy value. Now the energy is equal to HF, but we don't have F, we have wavelength, so that is equal to HC over lambda. Now the energy therefore we have is 6.626 by 10 to the power of negative 34. We multiply that by 3 by 10 to the power of 8, which is the speed of light, and on the bottom we have our wavelength, which is 650 nanometers, so we multiply that by 10 to the negative 9, and therefore we get an answer there of the energy here of 3.06 by 10 to the power of negative 19 joules. Now this energy here of 3.06 by 10 to the negative 19 tells the energy of one single photon here. Now we're told here we've got 30 milliwatts, which means 30 millijoules per second. So that's the value of the total energy we're going to use. So we get 30 millijoules per second. So that means 30 by 10 to the negative 3 joules. And we divide this by the individual photon value, which is 3.06 by 10 to the negative 19, and that will give us the total number of photons being emitted. And that gives me a value of 9.8 by 10 to the power of 16 photons. Now, if you look at the responses, B therefore becomes my only answer. So in this question, we're dealing with Young's double slit experiment, where we have diffraction taking place, and we have monochromatic light producing a series of maxima on the far wall here. This is going to be our length L, and of course this point 0.08 is going to be the separation between the central maximum and the first maximum, which we're going to call Y. Now the path that these lights travel is going to be like this, and I'm going to draw this as accurate as I can. I'm pretty slack in drawing straight lines, but here we have two paths and we're getting here maxima here, so that means we're getting constructive interference. That tells us here that if this is L dash and this is L, and this is going to be equal to the path that these two light beams travel, then the difference in the distances between these two is exactly one wavelength. Now that means that angle there is related to the slit separation and that one wavelength, and that's what this formula is all about. But we can't measure that angle very precisely, so what we rely on is that if we then use simple trigonometry, then, and as long as the distances here are large, then what we're able to do is we can say this distance here, which is our L, and this maxima here will produce an angle that is roughly the same angle as the inside here. So then what we say is that my tan of the angle is going to be equal to the y over L, which is our 0.08 over the length, which is 0.3. That allows me to work out the angle, so therefore the angle becomes the inverse tan of 0.08 over 0.3. Now, that tells us here my options are A in this case and C in this case. Now, what is D? D is the slit separation, so that's 1 micrometer, so the answer becomes C. And now we're going into a short answer question. Our first question here involves the quantum nature of light. So what we have here is a student is investigating the photoelectric effect, and the frequency of light incident on a metal surface was varied, and the corresponding maximum kinetic energy of the photoelectrons were measured, and these are the values they got. And then it says plot the results on the axis below, well, it's actually to our right here, and hence determine the work function of the metal in electron volts. Now, when you are plotting a graph, do some good techniques. First of all, make sure you read it properly, but also do little X's to show precisely where your points are. So our frequency is 11.2, so that becomes, if this is separated here by a value of 1, 2, 3, 4, 5, you know that each section here is going to be equal to 0.4. So 11.2 gives us a value here, but on our y-axis it's 0.6, so moving that up to 0.6 we get a value here. So there's our first point. Our second point, I'm going to do the other ones relatively quickly. So there are my points. Now what you do, of course, is a line of best fit. Now I'm going to draw that like so. You'll note that my line of best fit does not pass through any of my points. It's the best average, and I've got some points above and some below. So it's important that when you do a line of best fit, you do not put all the line in such a way that it's on either side of the dot points, but it's a good approximation for all the points. It's important also for this question to extrapolate. So in other words, pass this line through, because we're going to also have to determine the work function. So what is the work function? Well, the work function is the minimum energy required to release photoelectrons. And if you remember your mathematics, is that the kinetic energy of our electron is equal to the photon energy minus the work function, which we're just going to call W. Now this can sometimes also be written as HF minus HF naught, where F is the threshold frequency. Now, the threshold frequency is this value right there. But it can also, the work function can also be determined by the fact that this is a form of the equation of y is equal to mx plus b, and it has the stopping voltage is going to also be our y-intercept. So if you wanted to work out what this frequency is and then multiply it by h, you're going to get the same value as if you're going to just simply read off your y-intercept, which is -4. So in this case, our work function is equal to -4 electron volts. Our next question, 25, really involves the model as predicted by Maxwell of electromagnetic radiation. So this diagram shows this model, and then we're having to relate this model to the predictions made by Maxwell. Before you start writing, understand what this model is saying. So let's go through it. We have here an oscillating charge. Now, charge has an electric field. That means as the charge oscillates up and down, it produces an oscillating electric field. Now, the fact that we have an oscillating electric field, Maxwell's equations show that an electric field that's changing produces a magnetic field, and that magnetic field also produces an electric field, which is equation number 4 in terms of Maxwell's equations. So what in essence this is saying is that the generation of the electric field causes the production of a magnetic field, which causes the production of an electric field, and so this becomes self-propagating. That is, once you start this process on, the actual changing electric field, magnetic field self-propagates, and this propagates as a wave, as demonstrated here by this diagram, because we have a classic wave shape here in terms of the electric field. So that's an important distinction because that is a prediction made by Maxwell. Maxwell basically said, look, because you have an oscillating charge, that produces a self-propagating wave of electromagnetic waves. So there is our first prediction, but we're relating it to our diagram. Because it's a wave, it has a wavelength associated with it, and of course it also has an amplitude associated with it as well, and the frequency. The second part of this diagram shows this aspect over here of V. What Maxwell discovered is that this self-propagating phenomena can only happen at a very specific speed. And he worked out with some mathematics that the speed of this wave ends up being the square root of mu naught E naught. That is the permeability of free space multiplied by the permittivity of free space, multiplied together the square root and then the inverse of that. That's the only speed that this can actually happen. Well, that ends up being 3 by 10 to the power of 8. So that's our second prediction, that the self-propagating wave of these electric fields, magnetic fields, can only happen at a particular speed, which in our case, of course, is the speed of light, and therefore predicted that light is a form of electromagnetic wave. So in order to get the full 4 marks, you need to talk about at least 2 predictions. The fact that this is plural is important. So the first prediction is the fact that this is an electromagnetic wave. We have the production of waves. Now we need to relate it to the model. That is, the oscillating charge produces an oscillating electric field which produces a magnetic field and so forth. So you must connect it back to the diagram. Our second prediction, of course, was the fact that this wave travels at a set speed, which is the speed of light. And as a result, he was able to not only say light is a form of electromagnetic radiation and traveling at this speed, but he also predicted that there would be other forms of electromagnetic waves which would also travel at the same speed but would not necessarily be light. And that was later on confirmed by the experiments of Hertz and many others later on. So here's question 27, and we asked to outline a thought experiment that relates to the prediction of time dilation. And then second half looks at outline experimental evidence that validates the prediction of time dilation. So we're really looking here, like the previous question we discussed, about some sort of modeling of time dilation, and then later on looking at some experimental data that validates that particular model. And that's again a very important process of science. You have a model which sort of describes and tries to explain certain behavior and then provide experimental evidence that validates that particular model. Now, this is a thought experiment. It's not really an experiment. It's just a way of modeling to help understand time dilation. So don't get confused that this is some sort of experimental technique. It isn't. It's just a thought experiment, which means it's just a way of thinking to look at the consequences of your model. And the best model here to discuss is our light pulse on a train. So what we'll have is we'll have a train that is moving left to right. And let's say in our case here that you are a person on the train. So we're going to just say here, let's say on the train. And then we're also dealing with what happens as the train moves of someone who's standing off the train. Now, we're going to have here a light pulse that bounces up and down. So the light pulse travels up and then comes back down again from a mirror. And so we know, simple mathematics says that since velocity is equals to distance over time, then the time that we have here, and let's say put this time naught, is equal to distance, which in this case is 2d, over the speed. Now the speed of light here, of course, is c, so we're going to have c here. So our t naught, the time of the light pulse going up and down, is equal to 2d over c. But what about the person seeing this off the train? The train is moving left to right because the train is moving in that direction. The train may end up being, let's say, over here by the time that light pulse comes back down again. So when that light pulse goes up and down, you're not seeing it going up and down, you're also seeing it going from left to right. So therefore, the actual path of the pulse you see is that path there. Now, Normally, what would we say is this is traveling in the same amount of time, and therefore the distance means that the speed is also faster, but that's not allowed. Our time here is equal to distance, and we're going to call this distance just for a different value here. We won't worry about the mathematics at this stage, but let's call this distance here equal to d, and this distance is the same d. We have 2d over, in this case, speed, which is c. Now you'll see here that 2d is definitely larger than our 2d over here, which means that if we were to compare the two times, t is larger than t naught. So we have a difference in times related to the person on the train and the related to the person off the train, which means we have here an example of a prediction of time dilation, because we're assuming that the speed is constant, and that's an important factor here. We have to say that the speed of light is constant to both observers. And so to get 4 marks, you need to outline this the basics here, but connect that here, as I've done here, to time dilation. Part B says outline experimental evidence that validates the prediction of time dilation. Now there's a couple of things here. Outlines a sketch in general terms, and you can talk about a number of experiments. There are 2 experiments you could really use that are discussed quite heavily in your textbooks. The first one is the production of muons by the bombardment of cosmic rays on our atmosphere, and the fact that they have a very short half-life, and yet they predominantly do make it through the atmosphere in a much longer time that is related to their half-life. So there's time dilations here. That's one experiment. The other experiment that you can discuss is the Keating experiment, which is really about the planes traveling around the globe at, let's say, here's my little plane here around the globe here, and it has a clock on here, a cesium atomic clock, and the clocks are synchronized to the stationary clocks that are remaining left on Earth. And as the plane goes around the Earth and comes back again, its time that it has elapsed is compared to the time that's elapsed to the stationary clock. And there is a difference. That is, the time on the plane is going to be smaller than the time on the ground. And so here, what we have here is a validation of the time dilation we've just discussed. So make sure you have a good understanding of muons or the Keating experiment, but they are 2 experimental evidences that validated the prediction of time dilation. So I hope that has helped you understand the questions from the 2019 paper for Module 7 type questions. In my final video on the HSC 2019, I'm going to be looking at questions related to Module 8, which is the universe to the atom, which really looks at questions relating to modern physics, particularly in terms of the nature of matter in itself. So stay tuned for that. I'm Paul from High School Physics Explained. Take care. Bye for now.